Hello class, this is Mr. Hart, and in this podcast we want to continue our unit on motion. We want to talk about a term called acceleration. Now we've been looking a lot at speed and velocity in the past lessons, and those terms are great and it's good values to find, but the problem is not a lot of things stay going at constant speed or velocity. Okay, they like to change their speed a lot, so that's why we need to talk about acceleration. Okay, so to help you kind of visualize what acceleration is, imagine one of those really nice luxury sport cars, okay, that they can zoom off the track. They can go from 0 to 60 in like 5 seconds, right? Those really nice cars. One of the reasons they're so nice is because of their ability to accelerate. They can go from stopped to a really fast speed in a short amount of time, right? So for example, my car's a pretty lame car. It probably goes 0 to 60 in like 2 minutes, okay? But both our cars will end up at the same speed, right? We'll both be going 60 miles per hour down the freeway or whatever it is, right? But that car can get there a lot faster or a lot quicker in a shorter amount of time. Okay, so acceleration is that term we use to describe how quickly something can change its speed. Okay, so our definition of acceleration is any change in speed or direction. Okay, or in other words, a change in velocity. Okay, so anytime something's speeding up or slowing down, it's changing its speed, it is accelerating. And the other one, the direction part, is a little bit confusing. We'll look at that in just a second. But anytime you're changing direction, it's also considered an acceleration. Okay. So let's start with a change in speed. That one makes intuitive sense, right? Anytime you're going from stopped to really fast, right, you're accelerating. You're causing this change in speed. Imagine, for example, runners coming out of the starter blocks, right? They're stopped, right? They're at a 0 velocity or 0 meters per second speed, and then all of a sudden they're moving really fast, right? They had to accelerate to change their speed. Okay. They also, at the end, they'll have to slow down as they're coming towards the end of the track, right? And that is also an acceleration. Some people call it deceleration. We'll just call it acceleration in the negative direction. Okay. But anytime you're changing speeds, speeding up, slowing down, that's an acceleration. Okay. So the change in speed is pretty intuitive to understand, but let's look at the change in direction and see if we can make sense of this. Okay. So let's imagine that you're running the 400-meter race. And the 400-meter race pretty much starts near the finish line. Okay, so you pretty much end up in the same place you start. Okay, but you go around the whole entire track. Okay, one full time. Okay, and obviously that's not a perfect lap, but anyways, you get the point, right? You start pretty much here, down here at the finish line. Go around once, you end up in the same place. Now, let's say you run that race at the exact same speed the entire time. Let's say you're running 6 meters per second the entire race. Okay? You're still accelerating, though, because you are moving in different directions as you go around the track. Okay? And the reason why we consider that an acceleration is it's not so much the change in speed, right? You're going the same speed the whole time, but your velocity is changing, right? Your velocity depends on that direction. And so because you are changing the direction of your velocity, like at this point, for example, your velocity would be going that direction, whereas at this point, it would be going this direction. So at different parts of the race, your velocity direction is changing, and thus we are accelerating. We're changing the direction of our velocity. Okay? So any type of change in velocity is considered an acceleration. So that's why when you change your direction, it's also considered an acceleration. Okay? So see if you can kind of wrap your mind around that one. It's a little bit harder to understand, but it's just any change in direction is also considered an acceleration. Okay? So there we go. That's our two definitions. Any change in speed or direction, okay? Or in other words, a change in your velocity. Okay, so when we're writing down this equation, it's very simple. Your acceleration is the change in velocity over the change in time, okay? So little a always represents acceleration when we're doing physics, okay? At least in this class. So little a is going to mean acceleration. V means velocity. And T always means time, okay? So acceleration equals your change in your velocity over the change in time, okay? Let's look at an example problem. So a sedan goes from 0 to 15 meters per second in 5 seconds. What is its acceleration? Okay, so all we need to do is find the change in velocity. Well, it went from 0 to 15, so our change in velocity is 15 meters per second. It did that in 5 seconds, so our change in time is also 5 seconds. And then we just plug into the equation. So acceleration equals change in velocity over change in time. That's going to be 15 meters per second over 5 seconds, which is going to give us 3. Now let's look at the units. Okay, meters per second per second. So we could write it like this, meters per second, okay? And that makes logical sense, right? They changed by 3 meters per second every second. They changed the velocity by 3 meters per second every second. But it doesn't make a whole lot of sense as far as writing it down. It kind of looks ugly. It's hard to explain to someone what that means. So we're going to do a shorthand version of this. Because we have meters per second over second, we can bring that second up here, and we can actually rewrite this as meters per second squared. Okay? So that means the exact same thing. Meters per second is the same thing as meters per second squared. Now, it doesn't really make a whole lot of sense to say a squared second in terms of, trying to explain to someone, but it makes the writing a lot easier, and it makes it, more neat and clean. So you can always read it and think of it in terms of meters per second, but when we write it as meters per second squared. Okay? But there you go. So your acceleration in this case is 3 meters per second squared. Okay? The car increased its speed by 3 meters per second every second. Okay? All right. Let's look at another example problem. So let's say we have this one. So sports car goes from 0 to 60 miles per hour in 5 seconds. What is its acceleration? In this case, because we have miles per hour, we have to convert it first, because otherwise we'll end up with miles per hour per second, and it's not really a nice unit to work with. So let's convert this first into units that we know. So we know that our change in velocity is 0 to 60 miles per hour, which is 60 miles per hour. Now let's do a quick conversion table. Okay. So 60 miles per hour, if you look at that unit sheet I handed out, you'll know that's the same as 2.24 or 2.24 miles per hour equals 1 meter per second. Okay. So you times that on your calculator and you get 26.79 meters per second. Okay. So now that's a unit we can work with. So let's give ourselves some more space. Okay, so now we know that the change in velocity is 60 miles per hour, which is equal to 26.79 meters per second. We put in that the change in time is still 5 seconds. And so acceleration equals change in velocity over change in time, which is equal to 26.79 meters per second over 5 seconds. You put that in your calculator, and you get that is equal to 5.36 meters per second squared. Okay? So there you go. So that car is accelerating at 5.36 meters per second squared, or 5.36 meters per second. All right, so we looked at some examples where the cars are speeding up. Let's look at an example where it's slowing down. Okay? So a truck is driving down the road at 14 meters per second. The driver sees a cow crossing the road and needs to stop before he hits it. If the brakes can accelerate the truck at -4 meters per second squared, okay, how long does it take the driver to stop? Okay. So just a note, sometimes you will see second squared written in this form with the caret symbol, kind of like you would type it in your calculator. Okay, so if you ever see that, that means second squared. Okay, but let's see what we know. We know that the car was going 14 meters per second and it has to stop. So that change in velocity is going to be a -14 meters per second. Okay, it was going 14 meters per second. It had to slow down to stop. That's a change of -14 meters per second. And we also know in this case the acceleration of the truck, okay, that can be applied by the brakes is -4 meters per second squared. So now we know acceleration and the change in velocity. We're trying to find the time. Okay, so let's rewrite our equation. So we have acceleration equals change in velocity over change in time. If we bring the time up here and bring the acceleration down there, we can rewrite this as the change in time equals the change in velocity over the acceleration. Okay, now that's something we can work with. We know the change in velocity and we know the acceleration. So we say that the change in velocity was negative 14 meters per second. And we know that the acceleration was negative 4 meters per second squared. You divide that on your calculator, and you'll get that that is 3.5 seconds. Okay, and if you think about that, look at the units. The meters per second will cancel out with a meters per second there, and you'll end up with 1 over 1 over 1 over a second. You do the math, and you'll end up with a second on top. Okay, so a velocity divided by acceleration does give you time, so that is the right unit, seconds. Okay, so what does that mean? That means the car took 3.5 seconds to stop. Okay, alrighty, so let's look at one other equation, and it comes from rewriting the initial acceleration equation. Okay, so if we start here with the acceleration equals the change in velocity over the change in time, we could bring the change in time over here to the acceleration. Okay, so we get acceleration times the change in time equals change in velocity. Now, change in velocity by definition of delta, right, means your final velocity minus your initial velocity. So you'll end up with acceleration times change in time equals the final velocity minus the initial velocity. Okay, so the last step, if we just add this initial velocity over to the other side, we get the equation written in terms of the final velocity. Okay, so the final velocity is equal to your initial velocity plus the acceleration times the change in time. Okay, and this is just a rewriting of that initial equation that we had, but this is such a common problem to find the final velocity that you'll see it written this way all the time. Okay, so I want you to be familiar with both of these versions because, yeah, they come from the same equation, but you'll see this one a whole lot. So you probably want to know this one as well as the other one. Okay, either form works. Okay, but VF is final velocity, VI is initial velocity, A is still acceleration, and T is still time. Okay, so you can use this equation or you can use the other one, whichever one makes more sense for the problem. Okay, this one's going to show up a whole lot when you're trying to find the final velocity. So let's look at an example problem where you're going to need to use this version of the equation as opposed to the other version of the equation. Okay, so for example, let's say a parked car accelerates at 9 meters per second squared for 12 seconds. What is its final velocity? Again, so looking right here, you can tell you're going to use the second version because it's asking you for the final velocity, not the acceleration. Okay, so what we're going to do is we're going to identify what we know. It tells us the acceleration of the car is 8 meters per second squared. It tells us that the change in time, or t, is equal to 12 seconds. And it doesn't tell us the initial velocity, but it says a parked car, right? Or it might say a stopped car or a car at rest. Those types of keywords are going to let you know that the initial velocity was 0 meters per second. Okay? So let's plug into that equation. The final velocity equals the initial velocity plus the acceleration times the change in time. Okay? In this case, the initial velocity is 0. The acceleration is 8 meters per second squared, and the time is 12 seconds. So that's going to give us 8 times 12, which is going to be 96. Now let's look at the units. You got a meter on top, you got a second, and you have that all over seconds squared. Well, one of the seconds on the bottom is going to cancel out with one of the seconds on the top, which is going to leave you with meters over seconds, which is what you would expect, right? This is a velocity or a speed, right? So that's going to be in meters per second. So there you go. So that car accelerates at 8 meters per second squared for 12 seconds. The final velocity is going to be 96 meters per second. Okay? Alrighty, so that's the homework for today, is doing these types of problems using both versions of the acceleration equation. Okay, so that's homework 2.5, and you'll just see some problems like these ones that we've been doing. Okay, so hopefully that helps. Let me know if you have any questions, and thank you for watching.